And so begins the final topic of the term. So today and the next day we're going to talk about multiple regression. Very often we're interested in simple one-to-one variable relationships, and when we talked about correlation and simple regression, that's what we were talking about. Okay, so let's say you have two variables, x and y. So you have these two variables, x and y, and you do a correlation, and you get a correlation of 0.5, okay? Which is high for the social sciences, for things like looking at personality variables, personality questionnaires, things like that. Real ones, not those Facebook ones, actual ones. Can we guess which Game of Thrones character you are based on the color of flower you enjoy? No, you can't. That's stupid. I once made one that said, can you guess which Dave Broadbeck you are based on your answer to this question? Are you Dave Broadbeck? Because then you're me. If not, go to hell. You just stop answering. But real ones, if you take a look at a single behavior and your score on some personality test, I haven't taken personality psychology in a long time. Give me a personality characteristic that's measured.
Neuroticism.
Okay, and what would be related to neuroticism?
Anxiety, negative.
No, give me behavior. When you score higher on neuroticism, what are you more likely to do?
Chew your nails.
There you go. That's good. By the way, I chewed my nails for 40 years. I stopped like a week ago, and I don't know why. And it's really weird. I have fingernails. Anyway, it's weird. I don't know what happened. Probably stopped taking heroin. Probably did it. So, you know what the correlation would be there? It's like 0.3 would be a really high one. We'd be very happy. A 0.3 correlation, by the way, looks roughly like you can hardly even see it. It sounds great. So that's probably close to a 0.4. Like, you can see there's a relationship there, but it's not that impressive. A 0.5, which is not that much more impressive than that, you might think, oh, that's wonderful. That is high, by the way. That's the kind of correlations we get with IQ in certain behaviors. We get with IQ and income. We get with IQ and salary, lifetime earnings. Excuse me. You get years of education, likelihood of getting into graduate school, stuff like that. We get 0.5, which sounds pretty good because it's like, well, it sounds like half, except it's not half. R is as you know from last time, R is the covariance of x and y divided by the standard deviation of x times the standard deviation of y. So the question you're asking then is how much variance in x is accounted for by variance in y. So, excuse me. Remember, covariance can have negatives and positives. It's not really a measure of variance per se. So in fact, R actually deals with standard deviations. So we have to square R to get variances. So R squared in this case, and I'm going to call it little r squared to differentiate it from something else that we'll talk about maybe today, but definitely by Tuesday, big R squared. Little r squared is only 0.25. In other words, you've accounted for a quarter of the variance, 25% of the variance. 75% left. So even these nice high correlations we get with IQ, which are sort of, IQ is so different than other personality variables that it's often considered an entirely different thing. It's, intelligence isn't considered a personality trait. It's studied differently. Wow. Because we account for a quarter of the variance in certain things. Ooh, science. So, that sounds good. This sounds, depends on how you frame the question. It also means there's 75% we haven't explained yet. That coffee went down my mind, jeez. Okay. There must be other variables that account for the rest of the variance. There have to be. Yes? Makes sense, yeah? We may not know what they are, but they must be out there. They're somewhere out there. Celine Dion, is that who that was? She sings somewhere out there? I hate her music. Boy, can she sing. I can't stand her. I believe everything she does is melodramatic. Like I get when she gets up in the morning and asks, is there any coffee? It's probably over dramatic and just syrupy and dripping with fake authenticity. Or fake fanticity, I believe is the official term for that. Fake fanticity. Thank you. We deal with this by actually bringing those other variables into the model. It's analogous to what we do. Remember I talked about when I first introduced the idea of factorial analysis of variance, and I said, what level of processing do you do the retention level experiment at, and vice versa? Well, why not just do both? Right? Why can't we have both? So you bring them into the model. So it looks like this. So there's the variance in y. The hardest part about all of this stuff is going to be thinking about variance as a thing. As an object you can touch and hold and nurture and love. Well, not the last two, but something you can actually experience, something you can imagine. Variance is a hard thing to imagine existing. I can think of it mathematically. I can think of it this way because I'm thinking about this stuff for a long time. But this circle is all the variance in y. That's what it represents. And then we have x1. The overlap is how we're explaining variance in y with variance in x1. So if y is lifetime salary or something like that. Lifetime earnings. And x1 is IQ. It's your score on the Western Adult Intelligence Scale. We're going to account for it, and that's about a quarter. I don't know if I made it perfectly nicely, but it's close. So there have to be other variables. What's another variable you think that maybe could relate to your lifetime earnings that isn't IQ? I'm assuming we're talking about people living in Canada.
Years of schooling.
Years of schooling. Probably relates also to IQ. Let's pretend it doesn't and doesn't overlap. But that's a good one. So we bring in x2. Now we've accounted for more variance in y. We've accounted for, as you notice here, unique variance in y. It's not this. It doesn't overlap here with x1. It's on its own. This is horrible. Like, how can people here see it? Is this in the way? Is that better? Or is that worse?
That is better,
Okay.
yeah.
Nice. I figured that out on the final day, eh? Final topic.
I was like,
Yeah, I noticed that. That's why I thought that must be in the way. You should have said something earlier.
why you can't draw a circle from the light? Do you want me to draw your circle?
You can't draw circles? How did you get into university?
Don't know.
There was no art component. That's art. So do you see what we've done here? I've had circles that are animated, and what they represent is variance. And the overlap is shared variance. And when we have shared variance, we've explained variance in one variable with variance in another. If we had height in centimeters as the y and height in inches as the x, they would be completely overlapping. Because the variance in one explains the variance in another. Make sense? Okay. That's so far. This is good, I hope. I think this is good. I like this picture. I also like the animations. They're fun. Okay. In general, what we end up with is a model. We always go back to having some kind of model. So y hat equals b sub 0. Remember yesterday or 2 days ago it was a. Let's change it to b again. So b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus dot 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 b sub p minus 1 x sub p minus 1 plus p. We have p minus 1 predictor variables. We have p parameters, because there's a b sub 0 that has no x. We have p minus 1 predictor variables. Okay. These shoes come untied constantly, and it is very strange.
Shoot your Velcros.
No, I love the classics.
Just don't apply them.
No, that's even worse than awful. They're too loose. They're too loose.
My kids' ones don't have laces.
I have size 11 and a half feet. They don't make kids shoes that size.
I have the kids on eBay.
They may be on eBay. Really giant kids for giant children.
You saw a guy who got like a giant slipper and he just used it as a bed.
No, I've
wanted
never
like a
seen-
size
You
like
have
really
those
size 110
You have
or
four?
like 1100.
That's good.
It was from China, so of course.
Well, see, there's a billion free people that are on Instagram that feet that.
Yeah, living in the mountains.
Yeah, that's right.
Goats.
That's pretty good.
That was funny. Living in the mountains. I don't know why that was as funny as I thought it was, but I spilled coffee all over my face. Okay. It was pretty good. It was pretty good. Okay, so we have p minus 1. Don't say why aren't there p predictors. It's not. There are p minus 1 predictors. There are p parameters, okay? Because this is also a parameter here. That's what, or it's a statistic in this case, but in model parlance, it's a parameter. Okay? Every year, someone's, why did you just call it p? Because it's not p. P is a measure of number of what we would probably call free parameters in the model. P minus 1 is the number of predictors, okay? So they really aren't parameters. I think of them as p standing for parameter. But I'm using that in a very loose term. In technical terminology, in other words, correctly, these are statistics, they aren't parameters. Okay? So far, so good? Okay. So in the population, in other words, here's what it looks like in the population. Here's the thing that's most akin to the structural model of analysis of variance, which is about parameters. They just become Greek letters and capital letters. Y equals beta 0 plus beta sub 1 x sub 1 plus beta sub 2 x sub 2 plus dot dot dot. Beta sub p minus 1 x sub p minus 1 plus epsilon. Okay. That's in the population. We can say a couple of things here that the errors are normally distributed independent with a mean of 0 and a variance of sigma squared sub epsilon. That should look familiar. That's exactly the same as it is in analysis of variance. In this case, epsilon is an error. It's individual variation. And that's, in fact, when you think about it, that's typically what it is in, it's we call it error, but really in analysis of variance too, it's, what I was saying, this is the level of being a human called being Enya, or being Maria, or being Samantha, or being Samantha. Oh, that's the last stage of that one. Right? So it's the same kind of thing. Okay? Good. And it's also, no, this is not predicted y. This is not y hat. This actually says this is how the world works. And a score equals. In other words, this is way more like the structural model of ANOVA than the other one with y hat and b's. These betas are a lot more like the alphas, betas, sigmas, whatever, not sigmas, deltas, gammas, and such in an ANOVA model. Those b's, b sub 0, b sub 1, b sub 2, You'll often hear them called betas, and that technically is incorrect. In fact, I believe when you get an output from SPSS, it says beta weights. They really aren't betas, but people have been calling that so long that it's stuck. It's like most facial tissue isn't Kleenex. It's just become that way. Everybody knows what it means, but technically they're Bs and these are betas, and you never really get the betas because they're population parameters. You can't know them. You're estimating the betas with the Bs. Just like we estimate the treatment effects with the values we get for, we're estimating tau in analysis of variance with the little treatment effects we figure out. Okay? Okay. So what we're trying to do then is bring in more variables into a model to make a better prediction. To make a better prediction. So what do we get? If p minus 1, we have p minus 1 predictions equals 1, sorry. So if p minus 1 predictors, we have one of those, we get a line. Okay. So here's, you get a line. We have one y variable and one x variable. Now, for those of you that haven't looked at this yet, if you have, don't spoil it. If we have 2, if p minus 1 equals 2, what do we get? We don't get a line anymore. What do we get?
Is it a curve?
No. No. Well, at least you tried. Thank you. So now we have a third variable. We've got x, y, well, x1 and x2. It's in 3 dimensions now. What do we get? I know some of you can see in front of you. Here's this. Use the last page that just says have a good summer on it.
You can use the other sheet.
No, it's okay. I can use ones with definitions. This is what matters. Okay, look. Pretend we don't have any third dimension. That's a line. Just this, that's all you can see. The universe. This is the universe. We have 2 dimensions. Now we have a third dimension. Oh, we get a surface or a plane. Okay. Remember learning Cartesian geometry, x, y coordinates in high school, right? Did you ever do 3 coordinate, x, y, z? Ever came up? Yeah. You've got equations of planes or surfaces. Okay. Now, what if p minus 1 is greater than 2? And again, if you're looking at it, that's no fun. I encourage you to look at them in advance. Don't misunderstand me, but I know you don't all have them in front of you. What would you think you'd get if p minus 1 was greater than 2? So in other words, you have at least 3 predictors. Maybe you have 5 predictors. Or 4, or 7. If you have 12, then whatever.
Would it be like a prism?
It's still a 3-dimensional object, right?
Oh, God.
Yeah. 4 dimensions.
And alternate universe?
Ooh, there you go. Alternate universe.
Break the fourth door.
What you have, in fact, classically, you would say you have something moving in time, and the other axis is time. So that's kind of hard to start to imagine.
Donnie Darko.
In fact, technically, what you get is something called a hyperplane in hyperspace, which is when you have to spin up the faster than light drive to get away from the Cylons.
It looks like outer space. Yeah, what does that look like?
I don't know.
Okay.
You can't imagine it. The only thing you can imagine is if you thought of time as time as the 4th dimension, it would look like this. So here's the surface, but because there's a variable time, it would be changing position all the time. Now, if you've got something that's got a very linear relationship and you deal with enough of this kind of data, you could actually kind of imagine it. But you have to have been doing it a long time and doing something that's there isn't a whole lot of change in time. So you would get something probably that would look like this. So there's your x and y, and then it would keep spinning.
Like the ballerinas on the eye things.
I don't even know what that means. You lost me. I believe you.
The gif online is like, which way do you think?
Yeah,
and it's like, is
the
it
legs.
spinning
Oh, I see.
right?
Yeah. Oh, that'll
Yeah.
leave
If
you.
you're
Yeah.
left brain, you see it go right, and if you're right brain, you see it go left. That's not actually true.
Yeah.
Of course it isn't,
just
because there's no left brain right there.
Confuse
Yeah.
yourself. You're like, I just see it
Yeah.
standing still.
But it's good if you're high. People have told me. It'll be legal soon. I'm stoned right now.
Same.
Yeah, good. We're talking about the same guy. So, that's funny. Because I just thought of it, there's no way I can tell you, and I will never say it out loud. But,
Just turn the mic off. It's okay.
no, I still can't, I can't even tell you without
Like
recording
on
it.
the chalkboard.
No, I can't do that either. I can't, I literally could not share this, no. But, it's not bad or anything, it's just something I shouldn't say. However, what if you have, some people say, what if you have more, and then you got color, it changes in color. I can't do that.
It's a mistake.
Yeah. At that point, your best bet is to not try to imagine hyperplanes and hyperspace, because you can't probably do it. Our universe has 3 dimensions clearly, and then the 4th being time, which if you other dimensions, no. Don't do that. It's bad for you. It'll blow your mind, man. It only
I'm having
works.
existential crisis.
Yeah. You're having an existential crisis. So it's like suddenly you're Kafka. Again, some of these, very often, many of these jokes are for me, so I can tell friends. Remember, was it the other day when I said it's science, you can't argue with it? And I said I was going to say that just so I could tell my friends that I do a podcast with? I did. That night we recorded. So, I got laughs from my 2 co-hosts and the 8 listeners we have. That one's pretty specialized. It's really just for us. We don't care if anyone listens. We record these other shows together, and then we realized we also talked about ridiculous shit over and over again. We just should record the rest of these conversations we're having, so we get those at mmvh.ca. Anyway, don't try to imagine. So I like imagining lines. I like imagining planes because I can do that. I can sometimes imagine moving planes, but that's pretty rare. I stopped trying to visualize stuff, and I like pictures for statistics. I think it's very useful. But don't do this. You can't. You can't think in 5 and 6 dimensional space. You just can't. It can't be imagined. Right? There's a reason in science fiction they can travel faster than the speed of light in hyperspace. You know why? Because you don't have to imagine it, because it's totally imaginary. It doesn't exist. You can just make up bullshit, which allows things to go really fast. Allows the humans to beat the Vorlons and the Shadows in Babylon 5. Spoiler alert, show ended in 1999, okay? It allows us to go faster than the speed of light. All that crap, that's bullshit. It's going faster than the speed of light, except in Star Trek, which is all true. You thought analysis of variance was gone. Just when you thought it was safe to go out. ANOVA returned. ANOVA, the reckoning. You can find out if your regression model is significant with analysis of variance, which makes sense. How much variance have we the question is asking, how much variance and why have we explained with variance and predictor variables? That sounds like a job for analysis of variance, Batman! I'm not sure if you're laughing at me or with me, or just because you're happy that it's almost finished. I suspect it's a little bit all 3 there. Variance due to regression. That's the model. That's the stuff after the y hat. Oh, and the intercept. And variance due to the residual. What's left over. You may have noticed, by the way, that when you do analysis of variance by SPSS, traditional analysis of variance using the GLM procedure. If when you played with that a little bit, I showed you that. It shows you something that says intercept and model. because the math that it's doing actually is regression. It's not doing traditional analysis of variance math. It comes out the same, which is cool. So we get variance to the residual and variance due to the regression model. Okay. Yep. Looks like this. It's a very simple analysis of variance. We get source of variation is regression or residual, that's left and total, of course. We get a sum of square, which I'm not even going to show you the calculate, don't worry about that. This is on the level of why would anyone do this by hand. The mean square is sum of squares regression over p minus 1 for regression. Sum of squares residual, that should be over n minus p, that's a typo. Sum of squares residual over n minus p. And then we take an f value, mean squared regression over mean squared residual.
Where should be n minus p?
This here.
Oh.
Sum of squares
Okay.
residual over n minus p. I don't know if that's just a mistake. Fix that. Okay. So sum of the squares, mean squared regression over mean squared residual. If you look, you get n minus 1 and p minus 1 and n minus p degrees of freedom. The n here, but you might wonder what's the n, because you've got, let's say you've got 500 cases, like records, and you've got 20 variables. Let's say at 500, n is 500. 500 records. It's not, it's the number of individual subjects you measure. Okay? Okay. Questions so far? It's not that bad. So this analysis is about the whole model. So y hat equals b sub 0 plus b sub 1 x sub 1 b sub 2 x sub 2. Let's say we have a 3 variable model, b sub 3 x sub 3. It tells you, are you explaining a significant amount of the variance in y with b sub 0 plus b sub 1 x sub 1, b sub 2 x sub 2, b sub 3 x sub 2. In other words, the whole thing. It's not about the individual x variables and the weights you put on them, the coefficients. It's about the whole thing. It's a sum of its parts. So what it's measuring then is, if we have a 3 variable model, it's saying, is that significant, the overlap? x1, x2, x3. It's not saying is x1 a significant amount, or x2 a significant amount, or x3 a significant amount, or x1 and x2, or x2 and x3, or x1 and x3, I think it's all the possibilities, or x1, x2, x3. No, that is what it's saying. All of them together. That's what it's at. That's the question that this ANOVA actually answers. Questions? And the b values that come out tell you how much to multiply the x value that you get by to, when you add it all together, figure out y. So of course the model is going to be significant. It never isn't. I mean, it just never isn't. It's going to explain enough variance that it's going to be, it's going to be non-zero. So if I can't think of 2 variables that don't correlate. At least a little tiny bit. When we add a bunch of them together, we're going to get enough that we can explain something. It may be trivial and uninteresting. We're going to get something. Get something. Okay? So of course the model is going to be significant. It doesn't happen that it isn't. What we're really interested in is, how how much extra variation in y is accounted for by adding another variable into the model. So if we have y hat equals b sub 0 plus b sub 1 x sub 1, and then we add in b sub 2 x sub 2, how much extra variation in y is accounted for by adding in variation in x? Because you've lost degrees of freedom whenever you do that. And whenever you bring in a variable, no matter what you're doing, what kind of stats you're doing, you lose degree of freedom. So that's a much more interesting and actually useful question. That's a useful question. The question of is the whole model going to be significant? Like, in other words, all the variables, of course it is. Of course it is. So think of it this way. Let's say we are explaining, let's get away from income and IQ. Let's move away from that. Let's explain something else. Okay, let's explain life expectancy. It's depressing, maybe. But yeah, we're all going to live forever. I'm going to live forever. It's my plan. So far, it's working out perfectly. There's a problem with inductive reasoning. Yeah, life expectancy. Give me two variables that correlate with life expectancy.
Drug use.
Yeah, but how are we going to quantify that?
I don't know.
No, it's okay.
Okay.
Let's think. How are we going to quantify it? Number of alcoholic drinks you have a day.
Sure.
It's good. Sure. I think it probably. I'm almost certain that those. Yeah, almost certain those correlate with it. Sadly, I'm stumbling because I drink a great deal. Give me another one. Positive or negative?
Eating a high cholesterol diet.
Okay. So you're saying if you eat more cholesterol, you don't live as long. I'm not sure that's even true, but I follow so little of that health stuff. Again, don't care. Let's pretend no.
Clog your arteries.
Clog your arteries. Isn't that more about, I don't care. Let's say it's about cholesterol. It is about cholesterol in your body. I mean, it's not necessarily about ingesting cholesterol. But that's a good one. But diet, drug use. Okay, good. Those are two good ones. We're going to explain a lot of variance now. Now let's bring in something that's ridiculous that has no real relationship to life expectancy, or a very small one. Give me something that has very little relationship to life expectancy.
Shoe size.
Shoe size. Perfect. That's a really good example.
Thank you.
No, it really is. It's almost it's like earlobe area will be another great one.
Whether or not your earlobes are attached.
I know, but that's just that because you can have earlobes that are attached to your like that, or you can have.
What are mine?
Look at mine.
You can have normal earlobes like we do, or you can have. Apparently, maybe Maria has weird earlobes.
Yeah, they're like fully attached.
So mine aren't attached.
Yeah, don't forget it.
No, I didn't know that was a thing.
Donald Sutherland, end of division wise. Okay, yeah, earlobe size and shoe size. There's probably some very small correlation there, actually. There probably is some, because there always is something, but it's probably so minusculely unimportant that we wouldn't care. However, if we had a regression model that said we have how long you live equals some base number as your intercept plus some negative number times the number of alcoholic drinks you have a day, because it's going to drop it, plus some negative number again. Wow. We're thinking about things that kill us. But the amount of cholesterol you ingest, plus some really small number close to 0 times your shoe size, plus some really small number times the area of your earlobe. We would get a significant regression model. Would you feel confident publishing an article that said we can predict how long you live based on 4 key variables? Diet, alcohol, shoe size, and earlobe size. No, you wouldn't, would you? Because remember, because there's such small correlations, we would have a number very close to 0 as that B times your shoe size. That's no good. But the analysis of variance is so significant. Yeah, what about we just remove that? It's still significant, probably. We haven't accounted for enough extra variance. Whoops. We don't want to lose degrees of freedom and increase. I'm sorry. It's
No, that's the way.
now.
Fire hazard.
It's a fire hazard. I don't think it's a fire hazard unless there's like What do you have in that bag?
Explosions?
Explosions. Actually,
As you say it on the podcast.
that's right. Yes. Everyone run for your lives. This may be the last you hear from me.
This is not a bomb.
Call the police. So. I'm very scared. Okay, so. The good thing is, every year this is the YouTube video that gets the most watches because it's the most complicated stuff, and then so it gets outside the class. So now people all over the world. Yeah. No, if they listen to anything I've done before, they're using this kind of crap. No, you know what it is? This stuff isn't that interesting. I've got to do something. You would not feel comfortable adding in that extra variable. Your shoe size, is stupid. It explains a small amount of variance, but that B we put at the beginning that was calculated, you have to remember how it's calculated. It's kind of like the way B's calculated when you do single regression. It's really small. It's close to 0. It's a thing. Like it probably does matter at some level. Probably if you're really, 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 really huge, you don't live as long. I don't know, like 7'11" or something. I don't know. So you have bigger earlobes and bigger shoes. Maybe. There's probably something there. It's probably so
usually.
vanishingly small.
Think of like freak shows.
You take everything into the strangest place, which I love. I'm so glad you're here. Like Manute Bol played professional basketball for the Washington Bullets, a couple other teams. He was 7'10". Yeah, he was. They found him in. He's Somali. No, he never played basketball before. A scout went to Somalia and found a really tall guy. His people were really tall people to begin with. And they find this guy, and they take him to the States to play college basketball. He was 160 pounds, and he was 7'10". All he did was drink milkshakes and do weights to gain weight. But he was so tall he got to play in the NBA. Yeah, he could dunk the ball like just without jumping. And he could block shots. He didn't have to jump. Just go. No, don't think so. No. And he eventually got okay at basketball. And he died at like 40 something. Doing relief work in his native Somalia. He was a pretty amazing guy. Manute Bol, Manutebol. Anyway. So we get a value for all the variables together, x1, x2, x3, and it's called big R squared, and that's going to be sum of squares regression over sum of squares total. That's one way to measure how much variance we've accounted for. Remember, little r squared talked about it does the same thing for just one variable and y. Here we've got 3 or 4 or 11 variables and y. Okay. So when we add a variable in, if you have a model of 5x variables, okay, 5 x's, so you got x1, x2, x3, x4, x5, and you add in a 6th x, does r squared go up? It has, well, it may, or maybe hugely, but or maybe it could be. No, it's not tricky. It could be that. So there's x4, and we'll put x5 here, and then maybe x6 is over here. It doesn't have overlap at all. It could go up, not at all, but that's so vanishingly small probability that we say it doesn't happen.
Do eventually they cover in some 100%?
Well, once you explain all the variants, but you never
so you wouldn't have like 300 variables that...
You might, but is that useful? This is a question you can ask yourself. Like, it gets so complicated to understand. If I give you an equation or regression model that has 300 variables to predict your life expectancy, and then we throw in shoe size and earlobe size, but if I can give you one that has 3 that explains almost the same amount of variance, the one with 3 is more useful. Yeah, right? So it has to go up, or it could stay the same. Theoretically, the chances are very small. So the question is, does it go up by enough to satisfy? Right? Does this extra variance you've accounted for, is it enough? You might say to yourself, Self, how much is enough? And that's a judgment call. Oh, that's interesting. There is a cutoff that's typically used. Is it a significant amount of variance? But even then, if our first three variables account for a great deal and our fourth one's still technically, statistically significant, using a test I'll show you in a second, but it's so small that it doesn't matter practically, we probably wouldn't use it. Because you've lost a degree of freedom, and you've increased the complexity of your model. Think about this. If you go from a two-variable model, which is a surface, you can actually draw a 3D surface. Well, I can't. But I can get a printer to do it. I can take software and put two predictor variables in and a y, and it'll draw a plane. It'll be on two-dimensional paper, obviously, but it looks three-dimensional. Or I could give you 3D glasses. I don't know. But, so that's one level of complexity. If I add one more variable, it suddenly becomes way more complicated. So that's something. Every time you add another variable, especially going from 2 to 3, especially going from something you can draw to something you literally cannot draw, going from a plane to a hyperplane, that's a big step. And remember, we're trying to communicate our results to the humans. They paid for it. Right? They paid for our research. Thank you, taxpayers of Canada. So let's try to communicate our results to them. And we make it so it's so hard for them to understand that they can't read it and they can't understand it without having to have an advanced degree in statistics. What use is it? We haven't helped anybody at a very practical level. There's practical significance and statistical significance. They're the same thing. It's nice when they are. They usually aren't. So we need something other than our big R squared, because R squared keeps going up. We can't say, oh, it keeps going up, we're happy. Because we're idiots. I'm never going to ask you how to calculate this, don't worry. But this thing is called adjusted R squared, and it's weighted by the number of predictors, right, and the number of observations. So it actually can go up and down. Yay! It's still pretty crude, but at least it can go up and down. At least if we add another variable and calculate this again, this thing can actually go down. That's a valuable thing. Because at least it tells us, oh, this is a kind of a mathematical way, an algorithm really, of saying, is it worth adding in another variable? It's not perfect, it's very crude, but it's way better than R squared, because R squared is always going to go up. Adjusted R squared doesn't always go up, sometimes it drops. So in this case, let's say we threw in, so we got the diet question, and we got the alcohol consumption question, and then we throw in the data about the shoe size, and it actually drops. Adjusted R squared drops. No, let's not put that in. Whereas with regular R squared, it would go up. So you'll see when you're building a regression model, any software will give you adjusted R squared. It'll give you the R squared because, well, you can also calculate it by just calculate and look at the ANOVA table. But it'll always give you adjusted R squareds. It's very useful. You can probably guess that the way you end up building these models is getting a whole bunch of different models and picking the best one. Oh, look, there's 15 points on the final exam about that. Questions so far? Even though you might think to yourself, oh, that was like 4 slides ago, I shouldn't ask it. Ask it. You following me so far? I'm using way more examples than I usually do when I teach this stuff. So I'm trying to.
So, I'll ask one,
yes,
just
please.
kind of for the hell of it. So we always use big R squared when it's going to be multiple, and then are we ever going to have a question that's going to be a single variable?
How do you mean questions in the single? Oh, you mean like?
Yeah, like small r's.
They're so analogous that they're basically the same thing. One's just for simple linear regression, one's for multiple.
Oh, okay.
Yeah, so conceptually they're the same thing.
Okay.
Yeah.
Could you use big R squared with a single variable?
You can, it just ends up being equal to little r squared in that case.
Okay,
Yeah.
so it doesn't, like, you wouldn't be messing up on a test if you use big R squared in the wrong question, I guess, so to speak.
No, but if you use little r with multiple regression, well, you can't.
Yeah.
Yeah. All little r squareds are big R squareds, but not all big R squareds are little r squareds.
I got it.
Okay, make sense? Okay.
Yeah, literally.
And all men are Socrates. Nothing? Nobody? Okay. You guys didn't read any Greek philosophy?
I knew the bird one.
No? Bird was good.
I think he brought in a bird just to mess with Plato or something.
I can fake my way through almost anything academically. Oh, no, I've been doing this for a long time. I can just go, yeah, exactly. So, which of these is going to be the best model? This is a question, this is just the kind of question I might ask you. Well, it may not be the same format, but this is the kind of question that when you get in your final exam. Okay, here's a model that just has x1 in the model. When I say it just has x1, there's a y and there's an intercept. Okay, all that's there. I'm using shorthand. So if we've got, in this case, the model technically is y hat equals b sub 0 plus b sub 1 x sub 1 plus residual plus e. So here's our regression. Sum of squares is 50. Our residual sum of squares is 80. I didn't tell you anything about n's or anything about p's or anything. Put it over there. What about if we have x2 in the model? So in this case, we've got 30 and 100 for our residual. Notice something so far. Does anybody notice anything about these two models? They're both single variable models. This one does not have x1 in it, and this one does not have x2 as a predictor. Do you notice anything so far? Tell me if you don't. Let's bring in the x1, x2 variable model. So there's x1, x2. So this has both variables in the model, and of course y and an intercept. Which one's the best one? And why? But first, but before that, do you notice anything about this? About these three models that's similar? Models at all, but just even about these sorts of variation degrees of freedom.
SS equals, no, it would be the same because the SS for x1 equals 130 and the SS for x2 equals 130.
And for x1, x2 equals 130.
Oh yeah, that's what I was saying.
Sum of squares is 130. That's good. Glad you caught that. What it's saying here, that says, I'm calling you Nick, what Penny is saying, but what this says is that there's a total amount of variation available in y that can be explained. And and that value in this case is 130. 130 what? 130 sum of squares. Doesn't matter. Okay? Now, the regression source of variation tells us how much is being explained. A little more fine grained is the regression mean square tells us that, but even just looking at the sum of squares of this. Which model do you like the best? Or is there one that's the worst and we can remove it right away if we're making a decision? So right now we've got two variables, x1 and x2, and we've got y. We're trying to explain why. We just figured out, we did the math for all three models. We got these three analyses of variance. Which one sucks that we can remove? I guess the question is, which one explains the least variance?
Wouldn't we just want to keep x1, x2 because it has the most degrees of freedom? Or am I thinking backwards?
Actually, the problem here is that degrees of freedom are high, so it's harder to find significance.
So we get rid of that.
No, I wouldn't necessarily say that. Because look at the sum of squares, it's big compared to these two. But there's one that's bad. Not bad, one we can remove.
Is it x2?
Yeah, it's x2. It explains a smaller amount of variance. So now goes between x1 and x1, x2. Is the jump from 50 up to 80 out of 130 total sum of squares, is that enough? It's actually a pretty big jump. If you just calculated Rsquare, you'd know that it's actually a very large jump. So you'd probably go with this one, x1, x2. I can make an argument, which I will refute in a moment because it's something I haven't taught you yet, but I like this one because it's just a line. We have one predictor variable. It's just a line. Anybody can understand a line. Surfaces are a little harder. The thing is, I can still draw a surface, or I can get a computer program to draw a surface, but it's easier to understand a single line. Here's a question, though. X1 and X2 overlap. Are they explaining any of the same variance? In other words, does it look like, so there's Y, here's two possibilities. Does it look like this? Or does it look like this? Because if they overlap, we're not explaining unique variance. We're explaining the same thing twice, which isn't going to be very good. We want to explain unique variance, right? You would never have a model, take it to the extreme, you would never have a model that says your weight in kilograms equals your height in inches plus something times your height in centimeters. It's stupid. You're explaining the same. It's not helping you in any way. Ouch. So which one? Do you think these overlap? X1, X2, or they don't overlap? And there is an answer to this question. Look at those numbers in front of you. And when you say one or the other, I'm going to ask you why. Say they would overlap though?
Because like regression in X1 is greater than regression in X2.
Yeah, it just could be there's more overlap with X1 and Y than X2. In fact, that is what that means then.
Okay.
Yeah.
Because I guess like the difference between SS and X2 is greater than the one in like X1.
Yeah, but that's all. It just means that, well, all that this is telling you is if it's 50 out of 130 and 30 out of 130, that there's more overlap between X1 and Y than there is between X2 and Y.
Okay, so it's kind of like a percentage, like
It's exactly a percentage. Not just kind of like, it's exactly a percentage. In fact, that's what Rsquare is. Well, it's a proportion. Okay. So look at that now. Look at the numbers. And he's along the right path here. Look at the numbers, the sum of squares for regression for those three models. Do you think they overlap or not, X1 and X2? And there is a way to figure this out. Or do you want me to tell you? Because soon we're gonna be losing listeners.
Oh, so.
I think I saw the light bulb.
Because I'm gonna say it's gonna be the other one because the top one because 50 covers whatever percentage of 130 and then 30 covers less, whereas 100 covers like a lot, but 80 still covers less than 100.
You were so close. You were so close. 50
plus 30 plus 80. I was just thinking that like you were saying.
Yeah. No.
You got there.
Stand on the shoulders of giants, as Isaac Newton said.
I'm 5'5".
Makes her Isaac Newton. So if you need any help with your calculus or physics homework, look, it's unique variance. 50, 80, 30, 100, still 130. It's always going to add up the same. But if this plus this is this, that means it's got to be like this one I'm talking.
Oh, okay. Sorry.
And that's great.
Just got it.
We have accounted for unique variance. Unique variance. You guys are always doing your own show back here. I think it's great. You seem to be having fun, so you're doing okay, so I'm not worried. I'm always concerned that I've done something horrible and you're laughing at me. But that's okay. Because I'm really quite self-centered. We want to account for unique variance. We don't want overlap. I choose this one. It's pretty rare when you get, in fact, this is so cooked up, this doesn't happen. This is in the best of all possible worlds, which we don't live in.
Can I ask a question?
Please.
So then how come for residual it's 50 and not 180? Because then 80 is
It can't be more than 130. The total amount of variance in Y is all the sum of squares added up together.
Right, which is 130.
Yeah. So 80 and 50 is 130, 30 and 100 is 130, 80 and 50 is 130.
So do we always look at the top variable, or?
I would look at, see in this case, there's a way to do this that's a little more finer grained than that. And we'll get into it. In fact, when you're looking at sums of squares, remember we talked about type 1 and type 2 sums of squares with analysis of variance. The reason type 2 sums of squares are useful is they're useful in, remember I said it mattered what you put in a model when you did the math first? That's what you put in the model first. That's what matters. Type 1 sums of squares depend on the order variables go into the model. Type 2s don't. So let's say we have a 3-variable model, x1, x2, and x3. And again, there's also intercept, and there's also residual, and it's y equals some combination of those. Okay. So type 1 and type 2 sums of squares. Type 1 sums of squares depend on the order they go in. Type 2s don't. So, if it works like this. For 3 variables, the type 1 sum of squares for x1 is sum of squares for regression x1. Type 1 sum of squares for x2 is x1, x2. They're both in there because we put x1 in first, and x3 is all of them together. The type 2s are conditional. x1 given x2, x3, x2 given x1, x3, x3 given x1, x2. So, if we just had 2, the type 2 sum of squares here from this one here on the bottom right is, and we put x1 in first, would just be this amount here. It's the type 2 sum of squares simply measure extra variance with everything else being already in the model. That's the key thing to take home from that. Type 2 sums of squares measure extra variance, assuming all the other variables are in the model. And I think you can see how that is going to be the most useful thing that we can calculate. Not that you'd ever calculate yourself. It involves a great deal of matrix algebra. But a computer could do it. And if you get those values for all these different variables, it's going to tell you a unique variance that's added for a given variable. And that's what you want. You don't want any overlap. If you take a look at the model, there's nothing in there about relationships between the x variables at all. Right? It's all independent. It's this plus this plus this plus this. Not this plus this unless this is here. There's none of that crap. Questions? We'll stop a little early. I know this is pretty dense. And we will pick it up next time. Thanks, guys. Okay, so maybe we might get this finished up today. We're not in a rush, but we might get it done. It'd be nice if I actually had it plugged in so you could see it on the screen. So let's try that. And let's just see if it shows up now. And that would be good. There you go. Hey! So, we were talking about this, the idea of type 1 and type 2 sums of squares. The nice thing about these type 2 things is they give you that extra variance, which is what you're interested in. So it's the extra variance accounted for by adding x1 in, given x2, x3. Adding x2 in, given x1, x3. Adding x3 in, given x1, x2. So it's unique variance. Some of the people that came by today, I was drawing some pictures. And one of the ways to look at this is if you got like, you think that container holds all the y variance? That's all of y. So if we add x1, and then x2, and let's say x3, okay? So all this is doing is accounting for unique variance. Just x1 given x2, x3, just x2 given x3, x1. But the thing is, that is thinking, well, why is that any different than, but here's the deal. What if you have a situation like this, where once you add x1 in, when you add x2, actually someone actually overlaps with x1. So the thing you care about is just the extra variance accounted for. And that's what these nice type 2 sums of squares do. Okay. They're just a diagnostic tool. They're a diagnostic tool. Question so far? Okay. So make sure. So you might ask why you should care. Well, if there's no correlation between the variables, the type 1s equal the type 2s. You know what? You're not going to care a lot about this. It's more that if you were really looking closely at something, you might be looking at these type 1 and type 2 sums of squares. If there is a correlation, the type 1s don't equal the type 2s. That's the important thing. Sort of what I was showing here in my diagram. We'll talk a bit more about that in a couple of slides. But it's something that does matter because you don't really want them. When you're bringing in an extra level of complexity by bringing in an extra variable, it better explain enough extra variance for it to be worthwhile. So what can these things give you? Type 2 sums of squares give the extra variation accounted for by having a variable in the model given the others are already there. It's a conditional thing. Okay, so it just talks about extra variance. Extra variance, nothing else. This can give us something called the coefficient of partial determination, which is just a unique variance that a variable contributes to y, the thing you're trying to predict. It's sort of the opposite of big R squared. Big R squared is called the coefficient of multiple determination. This is the coefficient of partial determination. You may have heard of partial correlations, which are a correlation where you do correlate two variables, then you sort of statistically control for one of the variables by taking the variance that it accounts for and the x thing, the x predictor. How do you get that? I'll tell you in a sec. So we had this coefficient of partial determination gives us the extra variation accounted for by adding in another variable. Okay? In square, get a partial correlation, which is actually quite useful. So, again, it's just this extra bit, and it's now as a proportion. For the you three guys who were there this morning over in the TA room, what I was saying is accounting for this percentage of there. That's exactly what I was doing in my head. I was doing the coefficient of partial determination, which obviously is very difficult because it's just the proportion, this extra bit here, the proportion of extra variance accounted for by bringing a new variable in the model. That's all it is. I'm obviously caring a lot about extra variance that's accounted for, and I'm obviously caring a lot about overlap, about redundant variance. That's this stuff here where we have x1, and then we throw x2 in. Look, it's already explaining some of the x1 variance. Why does that matter? Think about the model. Here's the model. The waddle model. Y hat equals b sub 0, b sub 1 x sub 1 plus b sub 2 x sub 2 plus dot 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 plus b sub p minus 1 x sub p minus 1 plus e. Right? That's just the basic model for multiple regression. There's nothing in there at all but two variables being together. Nothing. Is there? Remember analysis of variance, we got like plus alpha beta, plus alpha gamma, plus beta gamma, plus alpha. There's none of that there. Because these coefficients aren't variables, these b's. They're just numbers that you multiply the value of the variable by. There's nothing in that model saying an x1, x2, like we would have with analysis of variance, alpha beta. There's nothing there. There's nothing about shared variance. In fact, there's even a name for this because it's a problem. And the problem is called multicollinearity. Multicollinearity is when you have shared variance between predictor variables in multiple regression. Multicollinearity is when you have shared variance between multiple predictor variables in multiple regression. Write that down. It sounds like a really good definition for a final exam.
Can you say it again?
I can.
Yeah.
Multicollinearity is when you have shared variance between predictor variables in multiple regression. And it's bad. Because there's nothing in the model that says it. One more time. I wonder if I'm even close to saying the same thing each time.
Just write it on the board.
I could, but you wouldn't be able to read my handwriting. So it really wouldn't be worth it. Multicollinearity, which is spelled right here, spelled just like it sounds, is when you have shared variance, or covariance if you want, between predictor variables in multiple regression. Except if it's Thursday. No, that's not. I threw that last part in, that isn't true. It's the same every day. See, now what's going to happen? If you have shared variance, where's it going to go? It's going to go here. Stuff you can't explain. That's not good. You never want that E or the epsilon or whatever in the model to be big. You want it to be small. You want to explain as much variance as you can. Suddenly we have extra variance we can't explain. That's no good. For we must explain variance. It is what we do. That's really all differential statistics is explaining variance. It really is all it is. Pretty much. Okay. Questions? Do you see why it's bad? Right? Because it's not here. When it's not in the model is like, this is how we are saying the universe works like this. The math then falls out of this. Oh, but you have an extra thing? Well, that screws everything up and makes this error, this thing you can't explain, bigger. You don't want big error. You want small error. So you're violating an assumption of the model, or of the procedure. It's the model assumption you're violating. It has nothing. It's a model assumption. It has nothing to do. There's no mention of overlapping variance. This will change the B's. That's the values of those what are called beta weights sometimes, or coefficients. I like coefficients better, but a lot of stats software calls them beta weights. So how do we detect multicollinearity? This is a problem because you can't. Drawing these pictures isn't the easiest thing to do. And those are just representations. They aren't really, you can't really draw pictures of variance. Well, the first thing you can do is look at correlations between x variables. Now, a lot of times when you're doing this kind of work with regression, you've got maybe 20 variables, 30 variables. I think I told you guys about my friend Todd doing this stuff where he was collecting data, trying to figure out how many cigarettes people smoke per day, using purely behavioral measures, not using anything invasive, not using saliva samples. Right. So what he did is he had 22 predictor variables and one predicted variable, which is cigarettes per day. And one of the things he had to do was build a regression model where he could predict cigarettes per day accurately. So it would be this times this, so it would be some number plus, I don't know, 5 times the number of years you smoked, which that's not what it was, but something, plus some other number times, have you tried to quit? Yes or no, 0 or 1, things like that. Well, you got 22 variables, some of them are going to overlap. So what you do is you do a correlation matrix between all of them, and you say, oh, these 2 variables correlate really highly. One of them we're going to have to throw away because they overlap so much. Which one do we throw away? Probably the one that doesn't correlate with Y, the thing we're trying to predict, so much. You're never going to get a case that is beautiful like this. This doesn't happen. This is in an idealized world, which we do not live in. There's a special case where it can happen, and we'll talk about that today. It's exceedingly rare. So you got to look at a correlation, look at correlations between X variables. It's the first thing to do. That's a lot of variables. You might have 20, 30 variables. And you're going to say, what's too high a correlation? I don't know. No one can give you an answer. 1.0 would be pretty high. It'd be like correlation of height in centimeters and height in inches. You wouldn't use both of those. But what about 0.2? That's actually a lot, but that wouldn't be uncommon. 0.3, I think about 0.3, I'd probably start going, we got to throw one of these in. So you're about to chuck something, just get rid of it. You got to take it. It's horrible because you collect these data and go, that's useless, man. Variable 7, you are dead to me. So you just throw it away. Well, you don't throw it away, you keep it. You always keep data. You just don't put it in the analysis. Okay, here's another assumption. We assume a linear model, which means straight lines. So a straight line, or when we get beyond lines and surfaces, a combination of things added together. It's linear. It's linear to each other. What if it's not linear? What if that is your model in the real world? Y equals lambda sub 0 plus lambda, to the lambda sub 1 times x times error. What if that's it? You know what that's an exponential. That's all it is. And there's a lot of things in science that are exponential. Like lots. Like, I don't know, here's an example. If we were to correlate dopamine to receptor binding efficiency and effective dose for 50% of the population for antipsychotic drugs, it looks like this. It's exponential. That's not a straight line. So this, I know this looks weird on the math level. Don't worry about that. The point here is that it's not straight. That's not a straight line because the exponent here. So you might look at that right now and just kind of go, ah! But there is a way to fix this. Just take the logarithm of both sides. And this is what you do. And in fact, when you look at a log scale on a graph, a lot of times, they'll have a log scale on the graph, and then it looks like a straight line, which all they've done there is a logarithm transformation. Because once you have log everything, you can then they all cancel each other out, and oh, look, it's just a linear regression. That's crazy. So that's something one could do. This is called an intrinsically linear regression. So an intrinsically linear regression is when you actually have you have something that isn't a straight line relationship, but can be easily transformed into one. Okay, so you have a a non-straight line relationship that can be easily transformed into one. And you can just take my word that logarithm thing I did worked. Wow, that's okay. look at something and say, oh, that looks like half of a parabola. Well, that means it's x squared. So just take the square root of both sides. And you might say to yourself, well, I don't know that. Yeah, you might not, but when you see a regular relationship in your data, go to somebody who's mathematically inclined and say, what does that kind of graph does that look like? And they'll look at it and say, oh, that's some kind of exponential, that's a parabola, whatever, and they can fix it for you. Or tell you how to fix it, which is just take the square root, or just take the logarithm, or maybe it looks like a sine curve. It's like, well, just take the arc sine of a straight line. Beautiful. So it's really doable. Okay? And in fact, exponentials are very common in science. We run into them all the time. And we just turn them into straight lines. We just turn them into straight lines by taking logarithms. So it's not a scary thing. Now, not everything is intrinsically linear. Some things just aren't linear. There's nothing you can do to them. So you just have to use a different kind of regression. You just don't fit a straight line anymore. Like if it was some sort of third-degree polynomial, there's no kind of transformation you can do to that turn into a straight line. And that's fine. You just fit a different kind of curve. That's, again, when you go to somebody who's way more mathematically inclined than you are, and you say, what does this look like to you? And they'll say, that's a third-degree polynomial. Okay, first explain to me what that is. No, actually don't. Can you turn that into a straight line? No, I can't, but I can fit a third-degree polynomial curve to it. Good, let's do that. It's the same logic. You're still minimizing residuals, squared residuals. You're just not fitting a straight line anymore if you don't have an intrinsically linear relationship. Okay? So back again to the idea of the additive model, there's no mention of interactions. How much time did we spend in ANOVA on interactions? Much time. We spent much time. You probably, look, a lot of times there are interactions. You probably could put something in, x1, x2. So x1 times x2. Yeah, I guess you could. To do that, though, you actually have to know that the interaction's there. It's kind of going ass backwards compared to ANOVA. But you can do this. And this is not, especially if you actually designed an experiment, we had, like, say, 2 levels of x1, 2 levels of x2. You can certainly put in x1, x2. There's nothing wrong with doing that. You typically don't, is all. It's really tough to know what this term should be, x1, x2. Should it be, let's say you have 5 variables. You have all 5 possible interactions, like x1, x2, x1, x2, x3, x1, x2, x4, x1, x2, x5, x2, x3, x2, blah, blah, blah. You do all that? No, you probably don't. So you really have to look at prior data and also your own data, do some EDA, to figure out what you might throw in as an interaction term. You typically wouldn't do this, by the way. I'm just telling you about it because it is sometimes done. You hardly ever see this. Okay. So what we are doing is we get this big data set, and we have to then select what our predictors are. What variables are we going to use? What kind of variables? Can you use qualitative data? Or as I like to call it, poorly defined quantitative data. In other words, let's say hair color. I don't know why you have a regression thing with hair color. Well, let's pretend. And let's pretend there are 4 colors of hair. So there's red, and there's blonde, and there's brown, and there's black. And I know it varies a lot more than that. I know people dye their hair, and I just don't care. We're going to pretend there are 4 colors of hair for this little idea. How shall we code the 4 colors of hair? Could you say 1 is blonde, and 2 is red, and 3 is brown, 4 is blue? Well, you could, but does it make any sense? This is a mathematical thing we're building. Does that mean that black hair is 4 times the hair of blonde hair? Well, that's weird. They're numbers, right? So you can't really do that. So you have to really be careful. There is a way to do this with qualitative data. It's hard. It's okay if it's binary. So if you've got something like I don't know, let's say one of the things we're trying to determine is how well people do in intro psych, and one of the variables is, are they a psych major? They get a 0 if they're not one, and a 1 if they are. That's easy. Because that actually makes sense. They are not a psych majors, they are 0 psych majors, or they are 1 psych major. We can do that. But we couldn't put in, are they a psych major, a sociology major, or a biology major? We couldn't do that because we didn't have 1, 2, 3. Or 0, 1. It wouldn't make any sense. It's hard to do. So if it's binary, it's easy. And remember, if you're doing it binary, it's 0 and 1, not 1 and 2. There actually is a way to do it. It's called dummy coding. And instead now of having one variable called major, we have a variable called psych, a variable called sociology, and a variable called biology. And if you're a psych major, this is you. And if you're a sociology major, this is you. And if you're a biology major, that's you. So now suddenly we've had one variable, 1 degree of freedom lost. Now we've lost 3 degrees of freedom. You got to really make this important. Others don't do this. It's something you very rarely would do. Okay? You understand how that works, though? So you can do it. People, it's not a good idea. It just isn't. It's not wrong. It's just that you're suddenly increasing the number of variables. You want to have as few variables as possible to make a prediction. We suddenly went from, and let's say it was major. There aren't just 3 majors here. There's probably like 18. Or some number like that. Want to go from 1 variable to 18 variables? No. You don't. You really don't. You can also watch it for Likert scales. We in psychology, not me in particular, but people out there that do that kind of psychology with the scales, think that if they put a number to something, suddenly they can do math on it. And I just don't use that with my other students as anybody. You understand? But if you score 26 on the Dave Broadbeck regression scale, which is just a series of questions that piss me off, is that twice as aggressive as someone who scores a 13? I don't know. Partially because I've just developed that scale right now. But even really well-established ones, we don't know. I would care for IQ, which is probably the most normalized psychological, probably is the most studied psychological trait, is the most tested psychological trait, probably the most reliable and valid psychological test. And also, I'm not sure that an IQ of 100 is twice the IQ of 50. In fact, I know it's way more than twice the intelligence. Right? Someone who's not an IQ of 50 is in real trouble for almost their life. I'm not some bad people. Or it's the difference between 70 and 100. 70 is you could probably, with some assistance, live by yourself. And 100 is the average person. And 130, I know people with IQs of 130 easily. I'm sure there are people in this room that have an IQ of at least 130. Is that difference? No, it's hard to hear. Volunteering your IQ is 130. We're gonna.
Isn't that really subjective though? Like people on the other side of the world that have just not.
Oh no, let's not worry about that right now. Let's not worry about the sort of biases in IQ tests. I'm talking about we're within this world here. Yeah, sure. I'm not talking about. And IQ tests get way better than they used to. There's still those questions, but they're better than they were 34 years ago. It's a good point, but let's say within Canada, that's not even at all people who can already speak English and have lived here for at least 10 years. I can keep narrowing it down until it's just me. So you got to watch out for these things. We love Likert scales in psychology. On a scale of 1 to 7, and I don't know that 7 is 6 more, or the difference between 7 and a 6 is the same as the difference between a 4 or 5. I just don't know. But boy, do we love these things. We love them. You gotta be careful, that's all. Experimental variables can actually be great. So independent variables, and you got a 0 or a 1 on that. So we actually assign people to groups. So a 0 or a 1 on some independent variable. We're not going to have any multicollinearity there because we put people in different groups and tested them. So like if you have think of this, a design like this. Okay? And then, the classic between subjects design. A subject who's in here, we know their level of A, we know their level of B. That's easy. If they're numerical things, we can even dummy code it. They don't overlap ever. B1 and B2 don't overlap. A1 and A2 do not overlap. So sometimes you do. It's the thing is, you don't usually do this with experiments. It doesn't lend itself to that kind of analysis. People can do it. There's nothing wrong with it. Okay, so what we have to do now is build a model. So we have to come up with something that we can present in a paper and say, this variable is a combination of the following things. So how do you choose what variables to use? You're not going to use all 22, for example. There used to be an assignment in this course on doing multiple regression, which I eventually removed because it's the end of the term and eventually people just went insane. But I would actually give you that cigarette data. 500 records, 23 variables. And just the assignment was one sentence: find the best model. Have fun.
Thank you for not doing that.
I stopped doing it 5 years ago, and that's partially because it is a lot of work to do. I can tell you Lori Bloomfield did it when I taught her. I can tell you Dwayne Kia did it when I taught him. We'll be back next year. Other people. Everybody comes up. The weird thing is, if you do this properly, people would come up with 2 different models. One that had 4 variables or one that had 7. Both of them were defensible. Which is exactly what it was in the paper. Like the technical report, it wasn't published, which is great. So because people were like, let's go look up the article. Doesn't exist. It's a technical report. The Ontario Health Ministry. You can't find it. It's not online anywhere. It was like max sigs, min sig, quick today. It was like a linear combination of 4 things. It was beautiful. So it's different from ANOVA. In ANOVA, we're like saying, is there an effect? Here we're saying the world works like this. It's a linear combination of these. At the deep level, at the math level, it's actually almost exactly the same. But on the sort of macro level, the 10,000 yard stair level, mixing things up there, it's a bit different. So you usually start out with a lot of variables. Like a lot of variables. Like I said, 20, 30. Okay. Well, you could do all possible regressions, which you can tell SPSS to do, by the way. This is really pretty easy. The problem is, let's say if there's 3 variables, x1, x2, x3, there are 7 models. Without throwing you interactions and crap. There are 7 different models. Well, you know what? I could look at all 7. That's something I can do. If there are 4 variables, there are 15. Well, yeah, 15 I could compare. For 10, I believe the number is a zillion. It's a ridiculous. I remember giving this assignment, and students were allotted 200 printed pages for the term, for the course. This was when I was teaching this at U of T, and I did the same assignment. I was a grad student, and I said, everybody got 200 pages. And I said, now find the best model. And people were using the all-reg procedure, all possible regressions. And actually, they made entire computer systems for the University of Toronto crash. I got getting phone calls to that from the IT administrators. Dave Broadbeck there? Yeah. Right here. Did you have your students try to crash her? No, I told them specifically not to do this. But like 5 or 8 people or 40 people in the class. Oh, let's see what happens if I do it. Harvard of the North. So you can't do this. You can't. right? It's an okay thing when you got 3 or 4 variable models, 3 or 4 variables. That's fine. But when you get to 10 and 20, I think I calculated to do 20, it would take all the paper ever made by humans for the printouts. It's some crazy thing. So, one of the things you can use to throw variables at, one of the things you can use to predict, to choose if variables are okay, you can use residual plots. So take the variable itself and regress it on its own with y. You can find anomalies, like you might find some weird coded number doesn't look right, so you have to remove that record. So this is a lot of this is exploratory data analysis. Or you might find that you have a curve and not a straight line. Curve, not a straight line. Okay. So nonlinear relationships. Okay, so how would you choose variables? Because again, let's say you've got 20. You think to yourself, Dave, there's got to be some automatic ways to do this. There are. One's called forward selection. What forward selection does is it's automatic, it's an algorithm. We start with the x value that has the highest R-squared, which is the biggest overlap with y. And then you add the next variable that gives the next biggest jump in R-squared. You can see why doing this up by hand would usually be a hellish nightmare. So you do this with a computer. You keep going until the jump in R-squared is not big enough. And what you do is you don't touch the defaults of the computer because it's put there for a reason. Usually it's like, is it a significant amount? At some point, it just stops. I'll show you something that does this. It calculates this f value because these are all variances. I'm never going to ask you how to do this or worry about this formula. But what it shows you, it calculates something called f star. So f star is mean squared regression for x1 given x2. That's extra variance divided by the total amount of variance. So in other words, it's this, oh, it's gone now, but it's that extra bit. That's all it's calculating, and is it significant? That's what F star is. That's what F star is. That's all it's doing, it's calculating, and then when F star gets below a certain threshold, it says, nope, done, here's a model. Enjoy. Every stats package that does regression does forward selection. They all have it available as an option. Do you understand how forward selection works? So you got all the variance in y, then it takes the way it explains the biggest variance, the x with the biggest overlap, then the next biggest, until it's not stopping here. Okay? Then there's backwards elimination. Guess how this works? Exactly the opposite way. It takes all the variables, let's say it's a 20 variable data set, it takes all 20, puts them all in the model, and starts removing variables that contribute the least amount of variance. It uses f star again. And it goes, oh, insignificant, divide, insignificant, divide, insignificant, we take out this, we now take out a significant amount of variance. Stop, here's your model. So it takes one of the smallest f star each time until it starts taking out something that takes a significant amount of variance out, and it stops. It says, here's a model for you, determined with backwards elimination. You understand how that one works? It's just the opposite of forward selection. Then there's stepwise. You know what? It's weird. Sometimes if you do forward and you do backward, they don't agree. In fact, almost always. Right? Then you do something called stepwise regression, which people think is magic. It combines the two. You go forward, so you put variables in, but every time you put a variable in, you then test by taking out each variable and see what happens. So after you put the second one in, take it out again and just see if did it make the amount of variance go down too much. So f star for each variable, and then take out ones that don't explain enough. It drops and adds if necessary, you've got an F to enter and an F to exit. Basically, the model. There you'd never screw it up, because if you make F with F to exit bigger than F with enter, it just keeps putting it in, take it out, put it in, take it out, put it in, take it out, and just gets stopped. That's what another thing that happened with my students. So I told them at U of T, who I told specifically not to do that. The entire mainframe for the Arts and Science building was down. They kept calling me. It's as simple as computer science. I showed them how to do it. Oh, I wonder what happens if I do this. Maybe Dave will give me extra points. I don't know what that voice is there I was doing there. It's the generic dumb guy who was from U of T. You set the criteria, and actually you don't set them. You just leave it alone, let the computer do it. They're set up with sensible defaults typically. So you got an F to enter, it's got to be greater than or equal to the F to leave. Okay, that sounds pretty good. You know what though? Those automatic methods only look at F's, only look at the overlap of variables. They don't look at anything else. All they look at is F to enter or F to leave, F stars. They never look at residual plots. So they don't care. They never look and see if something's curvilinear. They never look to see if you've got an outlier. They don't care about multicollinearity. They don't look at that and say, oh, well, don't use both these variables. They overlap by a little too much for my taste. They care about it in an indirect way, because if they overlap too much, it's not a big F star. Nonetheless. So they don't worry about anything that we would worry about as humans. So these algorithmic methods are fine, and I like them as a starting point. When I've done this, which is not very often, I do all three of those as a starting point, just to see what happens. Here's an approach, and this is an approach that I've taken over the years when I have played with this. And this is the one I would suggest if any of you are going to do this, I would like you to do it this way. Start with a correlation matrix. So every variable correlate with every variable. Just correlate everything. And now, take a subset of those predictor variables that do a good job predicting y, if you're trying to predict, and don't correlate too much with each other. What's too much? I can't answer that question. Though, as a rule, more than 0.2 kind of bugs me. But that's completely arbitrary. So let's say next year for your thesis, right? By the way, everybody, there are many of you who do thesis next year, but one of your classmates, Samantha, will be doing it on Friday, so you should go to NW 200 at 2:30 and see her and her classmates present their honors theses. And if you don't, the terrorists win, really. So, it was about 20 minutes after 9/11 when people said that seriously. That people went, that's crazy, let's stop saying that. But there was a time, about 20 minutes. So you should go see that. But many of you are going to try to do a thesis next year, and that's great. And I want you to, if you can, that's wonderful. And some of you might do regression. And if you do, get a bunch of variables, pick a subset of them that overlap, that predict y, that don't overlap with each other. So the x1, x2s, for example, x3s, the predictors, don't correlate with each other too much. Okay? If it's a small enough way to do it, I'd look at all the possible regressions. If you've got it down to 4 or 5 variables, just do all of them and look at them. So far, it will take you a day. And it literally will take you a day. You have to print these things out, because you have them on multiple screens. So you got to print out residual plots everywhere, and like sit on the floor of a room looking like a crazy person who believes in conspiracies. And you've got like residual plots everywhere and strings connecting them. Like Sunday Night's Homeland episode. Really like the big reveal in every episode of Homeland, every series of Homeland. If all three agree, you probably have something. All three hardly ever agree, but if they do, you probably okay. Check for outliers on residual plots. Check for curves on residual plots, or let's say, if you have a residual plot where, so there's the x and there's residuals, and the pattern looks like this, like a cone or something. So as x gets bigger, e gets bigger. That's a problem. There's supposed to be no relationship between x and the ax or residual. Then, you know what? You go away from it for a week and you do the whole thing again. Because a lot of times, because you're dealing with so much data, you're missing stuff. And you're dealing with so many plots, you're missing things. So you've got to put it away and come back to it. You want a model that doesn't overpredict any more than it underpredicts. And that's a hard thing to know. Is it biased in some way? Well, one of the things you can look at, a useful statistic that I don't think people look at enough, is something called C at P. Okay? And regression will do this, it'll look at this for you. A regression procedure will look at this. And you want it to have, it's called Mallow's CP sometimes. And what you want, the expected value of CP equals P. P is the number of parameters in the model, number of predictors plus 1. So if you've got a 4-variable model, what's C at P then? If you have an unbiased model, it's 5. 4 predictors is P minus 1, 5. Okay? So you're going to look at things like what the R-squared is. You're going to look at things like residual plots, but you're also going to look at measures like CP, which can be very useful. Any questions on that? All right. Now, I'm going to tell you something. And I'm going to stop recording.
Uh-oh.
No, I'm going to tell you something. Thanks, everybody.